This is section 7.8, acid-base neutralization reactions. We talked about this a little bit on Monday, so I'm just going to go through these first couple slides real quickly. Remember that acids form hydrogen ions in solution. We recognize them because their formulas begin with hydrogen. Bases are going to form hydroxide ions in solution, and so most of those that we're going to encounter are going to be metal hydroxides. Then this table showed us examples of some common ones. All of these acid formulas start with H. All of the base formulas end with OH. So that's how you can recognize those. We said that these were neutralization reactions, and they form water when you mix an acid and a base. The other product is called a salt, and that could be any ionic compound. So the general form here is an acid plus a base produces water and salt. The net ionic reaction for many of these is the same. Hydrogen ion plus hydroxide ion goes to water. And I'm just going to do an example of that to show you. So, name an acid. Hydrochloric acid, thank you. So, hydrochloric acid, name a base. Sodium hydroxide. Well, I should probably put state symbols in there. There's a fly on my iPad. What did I do? Okay, let's just start over. Yes, erase all strokes. Please, thank you. Okay, good grief. Just give me one of those dates. So, hydrochloric acid plus sodium hydroxide. Yeah, there we go. So we can approach predicting the products of acid-base reactions the same way that we did with the precipitation reactions. We know that acids ionize when they're aqueous, and so we get hydrogen ions and chloride ions. And these bases are soluble, and so they ionize as well, and so we switch the partners, and we end up with H plus pairing up with OH minus, and sodium pairing up with chloride. H and OH getting together is H2O. If you write HOH, I'll know what you mean, but I might snicker at you because it's kind of silly. Sodium and chloride, plus one, minus one, we just put them together, and that's a soluble compound. Then if we look at this, we realize that it's balanced, so we don't have to do that at all. Now, if we're going to write a net ionic reaction for this, let's see what we end up with. We're going to take the HCl apart because it's aqueous. Remember, when we're writing net ionic equations, we divide anything that's aqueous into its ions. Sodium hydroxide is also aqueous. And these are going to form liquid water. Water is not dissolved in water because water is water. So water's a liquid here. If the state symbol is a liquid, a gas, or a solid, you don't break it into ions. And then sodium chloride is aqueous. And so that is ions. This is the complete ionic equation, and this shows us what actually is present in the solution. We have hydrogen ions and chloride ions and sodium ions and hydroxide ions to start with. When we mix those, they react, and we end up with water molecules and sodium ions and chloride ions. That's the total ionic reaction or equation, complete ionic equation. So then to make the net ionic, we're going to remove the ions that are the same on both sides, which is the sodium ions and the chloride ions. And then we just rewrite what's left. And we end up with hydrogen ions plus hydroxide ions forming water. And that is going to be the net ionic equation for most acid-base reactions. It's always going to be the same. The pattern of these reactions is acid plus base yields water and salt. So let's write a molecular and a net ionic equation. Okay, I noticed this yesterday, and I'm just going to fix it right now. Fro the reaction, okay, not fro the reaction. Write a molecular and net ionic equation for the reaction that occurs between aqueous sulfuric acid and aqueous potassium hydroxide. So this will be real similar to what I just did. We need to write down these reactants. We've got H2SO4. And what should the state symbol for that be? AQ, because it says aqueous. And potassium hydroxide, KOH. That's also aqueous. And then these are going to react. What are they going to form? We have an acid, H2SO4, and we have a base, KOH. We're going to make water and an ionic compound. So we know that the first product is going to be water. Well, it's probably a good idea to write what these ions are below. We have hydrogen ions and sulfate ions. We have potassium ions and hydroxide ions. So the H plus and the OH minus are going to make the water. The other two ions are going to make this ionic compound. We're going to have K plus and SO4, 2 minus. So we have to consider the charges when we write the formula. We get K2SO4. With most acid-base reactions, the salt product is going to be soluble. Couldn't hurt to look it up in the table, and if we look it up, we see that it is soluble. That should go after it, but I ran out of screen. So there's our molecular equation. It should be balanced, though. Is it balanced? No. H2SO4 is what we call a diprotic acid because it has 2 hydrogen ions on it. So each of those hydrogen ions is going to need a hydroxide ion to react with. And so we can kind of anticipate that we're going to need 2 KOHs, or we can look at it the way we learned how to balance equations, which is look and see how many of each thing are on each side. Now, there's hydrogens in several places, there's oxygens in several places. So generally, I would advise you to leave those for last. They'll often take care of themselves. So think about the potassium and the sulfur and see if those are okay. Notice that sulfate is present as a reactant and as a product. So if you want to, you can balance that sulfate as a unit because that was a bundle pack, a polyatomic ion, and it didn't get changed, it didn't come apart. Sometimes polyatomic ions do come apart and they don't really show up in the products, but this one stays the same. And so we have 1 sulfate ion on the left side and 1 sulfate ion on the right side. Then if we look at the potassium, here we have 1 potassium here, and over here we have 2 of them. So that tells us we need to put a 2 in front of the KOH. It's an ugly 2. That's better. So now we've checked out the sulfur, the sulfate, and the potassiums, and now we need to look at the hydrogens and oxygens and see if they're okay. How many hydrogens are on the left side of the equation? 4. Total of 4. We have 2 in the sulfuric acid, and we have 2 KOH units, so that's a total of 4. How many hydrogens are on the right side? Only 2. So if we put a 2 in front of the H2O, that'll give us 4. And that's not going to mess up the potassium or the sulfur. Now we can look at the oxygens that are not in sulfate separately, or we can consider all the oxygens. It's going to end up being the same in either way. Here we have 2 oxygens in KOH because there's 2 of them, right? So there's 2 there, and there's 4 over in that sulfate. Over here we have 2 H2O molecules, so that gives us 2 oxygens, and there's 4 over there in the sulfate, and so this is a balanced equation. Now what is the net ionic equation? We could do this the long way, or we could do it the short way. What's the net ionic equation for pretty much any acid-base reaction? Hydrogen ion plus hydroxide ion gives water. But let's work it out the long way and prove that to ourselves. So writing net ionic equation, again, we take anything that's aqueous and we divide it up into ions. H2SO4. There is no H2 ion. Okay? That just means there's 2 hydrogen ions. So there's 2 hydrogen ions, and they have a +1 charge. And then we have sulfate. Okay, sometimes, and I saw this yesterday, a couple students were trying to do this, sometimes students say they want to break this up into 3 ions, hydrogen ions and sulfide ions and oxide ions. No. Each compound is 2 ions, 1 cation, 1 anion, okay? So whatever the first element is, cover that up. That's the first ion. The second ion is everything that's left. Okay, so if you're getting yourself in trouble, make sure that you're not doing that. So hydrogen and sulfate, and then the next one, the potassium and the hydroxide, is going to give us 2 potassium ions and 2 hydroxide ions. Write their charges. Liquid water, we don't divide that because it's a liquid. It's not aqueous. And then we have 2 potassium ions and a sulfate ion. So that would be the complete ionic equation, which the question didn't ask us for, but you may end up writing that as part of your work. Then we look to see what are the spectators. What ions were present as reactants and are present unchanged as products? Well, there's a sulfate over here, and there's a sulfate in the reactants. There's 2 potassium ions in the reactants and 2 potassium ions in the product. And then we're going to copy down everything that's left. 2H plus 2OH minus, yielding 2H2O. All those coefficients are 2's. The properly balanced chemical equation has the lowest ratio because, we could put 1,052 hydrogen ions and reacts with 1,052 hydroxide ions to form 1,052 water molecules. But why would we want to do that? We want the lowest. And so if we divide all of those by 2, we end up with 1s. So hydrogen ion plus hydroxide ion gives water. That's that same net ionic equation. So is it okay on a question like this to write the balanced molecular equation and then just write H plus OH minus goes to H2O? Absolutely. That's what it ends up. You need to be able to show your work. You need to be able to figure out what a net ionic equation is, but there's plenty of other places that you're going to have to demonstrate that. On mastering chemistry, you have to read the question carefully and see, do they want the state symbols? If they want the state symbols, you have to put the state symbols in. And like one of my students at COS found out, a capital S is not the same as lowercase s. Okay, it's like your password. It's case sensitive, right? It wants lowercase letters. And don't try to put a 1 in instead of an L, because it knows the difference, even if they look the same. Any questions? This is another section of section 7.8. Kind of seems like it should be a separate section, but it isn't, so we'll run it all together. Gas evolution reactions. Some reactions give off a gas. or we say they evolve a gas. A gas is produced as part of the reaction. Some of these form a gaseous product directly, like if you react sulfuric acid with lithium sulfide, you generate hydrogen sulfide gas and lithium sulfate. Hydrogen sulfide gas smells a lot like rotten eggs. Most sulfur-containing compounds don't smell good. Other reactions are going to form an intermediate product that will decompose into a gas. So if we react hydrochloric acid with baking soda, which is sodium hydrogen carbonate, what gets formed is carbonic acid, H2CO3. Carbonic acid is not stable, and so it's going to come apart all by itself. It's going to just fall apart, and it's going to fall apart into water and carbon dioxide. Carbonic acid is what they use to carbonate your soda. Put carbonic acid in there, and then it comes apart into carbon dioxide, which gives us those lovely fizzy bubbles, and water. Like, oh, they put acid in my soda. It decomposes into carbon dioxide and water. Both of those are pretty harmless in moderate quantities, so it's okay. These are the types of compounds that we need to know about. There are others, obviously. But these are the types of compounds that involve gas evolution reactions. So if you have a reactant that is a sulfide and you end up with a product that's H2S, you need to recognize that that's going to be a gas, hydrogen sulfide. So that one's kind of by itself. And here's an example down here. This table's too wide. It didn't fit. I was pointing at the wrong part of the screen. If we react hydrogen chloride or hydrochloric acid with potassium sulfide, okay, the best way to predict these things, what the products are, if they're ionic, is to just swap ions. So the hydrogen is going to go with the sulfur. You're going to end up with H2S. And then it's up to you to remember that H2S is a gas. That's not an aqueous substance, it's a gas, and it will bubble out and cause a stench. And that's why anything that evolves H2S, we always do in the fume hood, because nobody wants to smell that. The other three things are ones that form an intermediate product that's going to decompose. So if you have carbonates or bicarbonates, you can end up with carbonic acid, H2CO3, as your intermediate product. That's not stable. And what it does, let's see if I can write directly on here. What it does is it loses a water molecule. If you take H2 and O out of H2CO3, what's left? CO2. Hopefully we all recognize that CO2 is a gas. Carbon dioxide, it's what you exhale as a product of the metabolism that your body does. You inhale oxygen, you exhale carbon dioxide. H2SO3, sulfurous acid, does the same thing. This is formed when you react sulfites or bisulfites. And so this is also going to lose a water molecule. And what's left? You take H2O out of H2SO3. Both of those hydrogens are gone, and you have one less oxygen, and you get SO2. That's sulfur dioxide, which is another smelly gas. If you react ammonium compounds, you can end up with ammonium hydroxide. Ammonium hydroxide also decomposes by losing a water molecule. So you subtract 2 hydrogens and an oxygen from NH4OH, and what's left? 1 nitrogen and 3 hydrogens, and that's ammonia. Ammonia is a gas at room temperature. Ammonia doesn't smell good either. Now you can go to the store and you can buy a bottle of ammonia. Like, that looks like a liquid to me. It's a solution of ammonia. What it really is ammonium hydroxide. in water. It's a dilute solution, and it still smells really, really bad because it decomposes and gives off ammonia gas. So if you're going to clean with ammonia, you have to be really careful with that stuff. Have some good ventilation, or you're going to be in a world of hurt. So down below are examples of some reactions. Hydrochloric acid reacting with potassium carbonate. Switch the partners, you end up with hydrogen and carbonate. Hydrogen carbonate is this carbonic acid, and it's not stable. And so you have to recognize, oh, that's right, that's one of those, and it comes apart. And so the products are H2O and CO2. And then the other product is the potassium and the chlorine, so potassium chloride. Same thing with sulfite. Here's hydrochloric acid reacting with potassium sulfite. The sulfite and the hydrogen forms H2SO3, which falls apart into water and sulfur dioxide. So we write in our products water and sulfur dioxide, and then the remaining ions are going to form a salt. Ammonium chloride reacting with potassium hydroxide. When we switch partners, we get ammonium and hydroxide together, and potassium and chloride together. Ammonium hydroxide is one of these that falls apart. So instead of writing ammonium hydroxide as the product, we write water and ammonia. And Mastering Chemistry is going to care about those state symbols. Water's a liquid at room temperature, and these four compounds here are gases. Any questions? Yes?
I don't understand. I thought we couldn't change the subscripts when we were.
The question is I thought we couldn't change the subscripts. That's a good question. Here we're not changing the subscripts for the purposes of balancing an equation. We're recognizing that there's another reaction that's occurring. Okay? And so in the examples down here, they're not showing the intermediate step. They're just showing what it ends up as. And we're going to... Yeah, it's another one of those special things that you just have to remember. And, you know, I wish it wasn't that way, but I was listening to my fifth grader work on his, I guess they call it English language arts or something, and he was looking through his spelling words, and he had to classify them as these words alter their spelling when you add ed at the end. And these words change their spelling if you add ing at the end. And these words don't change. It's like, how did we remember that? You know? Denied. Okay, I denied. Deny is D-E-N-Y, but when you make the past tense, it's D-E-N-I-E-D. Well, there may be some of you that just didn't quite remember that, and you had spelling issues. And I understand that, and that's fine, and there's hope for you. My oldest son, who's now a junior chemistry major and doing well, when he was younger, I read one of his papers, and he misspelled who, W-H-O. He spelled who 3 different ways in one paragraph. And I'm like, oh my goodness, this child's going to be trouble. But no, he turned out fine. So there's hope for you. But we have all learned a lot of exceptions. The English language is full of things like this. And so, yes, it's annoying, but life is annoying sometimes. And so this is one of those things that you just kind of have to remember. Now, I will tell you, if you're wanting to get an A in this class, you better pay attention to that and remember it. Okay, if you're trying to pass the class, you could skip this part, this gas evolution reaction thing, because there's going to be like maybe one question on the exam. This is not a big deal. Dimensional analysis, unit conversions, moles to grams, molar masses, those things are huge deals. So if you're struggling with that, put your attention on the things that are most important. This is a small deal, okay? But we have to cover it. So here's the instructions for writing these sorts of equations. Write the skeletal equation with the reactants and products. You figure out the products by swapping ions. And then, oh, that's right, there's a typo in here too. I should have fixed it yesterday. This isn't SO2, it's SO3. There, now it's fixed. That H2CO3, H2SO3, and NH4OH are all going to decompose. They decompose by losing a water molecule, and then you can figure out their other product by just subtracting 2 hydrogens and an oxygen from their formulas. So you have to recognize that and then balance the equation. So let's do an example. Write a molecular equation for the gas evolution reaction that occurs when you mix aqueous hydrobromic acid and aqueous potassium sulfite. Good grief. What did I do? There we go. White pen. So hydrobromic acid. Well, that's one of those binary acids without oxygen. So it's HBr, and it's aqueous. The ions in that are hydrogen ion and bromide ion. And potassium sulfite. So sometimes it's helpful to write the ions below first and then put them together. Potassium is K+. Sulfite is the light version of sulfate. Sulfate is SO4, 2-. Sulfite is SO3, 2-. So when we put those two together, we need 2 potassiums with the sulfite. Good grief. Sulfate is so much more common that I tend to write that instead. That's aqueous. So we predict the products. This is going to be a big old mess. We predict the products by swapping partners. So we're going to put potassium and bromide together and see what happens. We're going to put hydrogen and sulfite together and see what happens. So I'm going to just, for grins, put the potassium first. Potassium and bromide, and then hydrogen and sulfite. Write those charges in there. They're important. So potassium and bromide, that's KBr. If we look that up, we see that that's aqueous. And H plus and sulfite, hopefully I can squeeze this in, is going to be H2SO3. And that's where the remembering part comes in. H2SO3, that's one of those guys that's unstable. So what does H2SO3 do? Well, I'm going to draw it up here. It loses a water molecule, so that's going to fall apart into water, and then look at what's left. You take the 2 H's off, and you take one of the oxygens off, and what you have left is SO2. And that's a gas. So this is the intermediate step that was missing in those examples in the table. It forms KBr and H2SO3, but the H2SO3 doesn't last very long. It falls apart. It's kind of like it's made out of, I'm blanking. There's Legos, and what are the other ones? The counterfeit ones. Not Mega Blocks. Maybe they are Mega Blocks. There's the off-brand of Legos. Mega Blocks, yeah. They don't stick together very well. I don't know if you've noticed that. I've banned them from my house. Okay, so then let's write this over again. I'm going to leave the state symbols out because I'm going to run out of room, and this isn't mastering chemistry. So HBr plus K2SO3 is going to form water and SO2 and KBr. Those are the products. Now, do you have to write that intermediate step in there? Not if you can do it in your head. You don't have to write it in there. But I'm thinking most of you will want to write it in there. And then look at this and ask yourself, is this balanced? Well, there's 1 hydrogen on the left and 2 on the right, so that's not good. We need to put a 2 over here. And then There's 2 bromines on the left now and only 1 on the right, so we need a 2 here. There's 2 potassiums on the left and 2 on the right, so that's okay. There's 1 sulfur on the left, 1 sulfur on the right. 3 oxygens on the left, and a total of 3 oxygens on the right. So there's 1 in the water and 2 in the SO2. So this is our molecular equation without the state symbols. H2O is a liquid, SO2 is a gas. Yes?
You have to put the equation in a certain like weight. Like,
Do I have to put the H2O first? No. No. Yeah, you could put the SO2 first, you could put the KBr first. It's like addition, the order doesn't matter. 1 plus 2 is 3, and 2 plus 1 is still 3. It shouldn't be a problem, no. I know mastering chemistry seems a little dense sometimes, but it's actually pretty sophisticated. So it should accept your reactants and products in whatever order you place them in, as long as you have your reactants on the left of the arrow and your products on the right of the arrow. Any other questions?